Hello, welcome to our webinar today. And the topic of our webinar today is the simulation of measurement systems in VirtualLab Fusion. And before we start, I want to introduce myself. My name is Stefan Steiner and I'm optical engineer at Lighttrans. Here you can see also my email address and our website. Now, if you have questions during the webinar, you can click the raise your hand button, and my colleague, Mr. Daniel Asobar, will answer your questions in the chat. After the webinar, there will also be the possibility to ask questions using your microphone. Now, before we start with the measurement systems, I want to introduce VirtualLab and show some of its concepts and capabilities. Now, in the context of measurement systems, and if we want to simulate such a complex system, optical system, we have at first different sources. For example, for the Mach-Zehnder interferometer, we use a monochromatic helium-neon laser, or for the Michelson interferometer we use a multichromatic white light source, and so on. So we have very different source types. And afterwards there are lots of possible optical components like lenses or dispersive elements which show some coherence effects. Then maybe there are components which where interference effects are of interest, or something like gratings, diffraction, which show diffractional effects. Then we have maybe optical fibers, and afterwards at the end we want to detect a signal. Now we have to choose an appropriate simulation technique for all these different kinds of propagations and components. And usually ray tracing is a very useful tool to simulate complex measurement systems or optical systems in common, but there are some restrictions in ray tracing due to the fact that the rays only have some informations. This is the position, the direction of the rays, and the optical path lengths. So we have problems if we want to simulate, for example, coherence effects or diffractional effects, as well as interference, which we need for the simulation of our interferometer measurement systems. So to summarize the limitations of classic field tracing, ray tracing, we have no chance to simulate interference effects, coherence of light, as well as diffraction. So for the simulation of complex measurement systems, we have to switch to physical optics simulation. And the approach of VirtualLab is that we use different modeling techniques for different components and different free space propagation steps. And this is the strategy of VirtualLab, and we call this field tracing. And with the help of field tracing, we can cover all these effects we need for the simulation of our measurement systems, such as interference, coherence, and diffraction. And we can also calculate field distributions, field amplitude, and phase. Now, as I mentioned, in order to simulate these complex optical systems, we need these different methods, and we can use them in one simulation process. And this is the approach of VirtualLab. Now let's start with the first example, the Mach-Zehnder interferometer. Before I start, I want to mention that you can find all these example files on our website. You just go to our website, lighttrans.com, and then go to Solution, Laser System Design, and here you find the measurement systems, and by clicking on More, you find the examples, as well the presentation and the sample files for VirtualLab. Now let's go back to the presentation. For the simulation of the Mach-Zehnder interferometer, we need some of the effects listed here. We want to simulate the interference pattern of this setup as well as the field distribution. So we are going to use field tracing to simulate these effects. Now the Mach-Zehnder interferometer is an optical setup where we have two identical beam lines, and this enables to measure the relative phase shifts between these beam lines. We have the reference path here, where we can put, for example, a phase delaying element, and we have a measurement path where we can put an object we want to investigate. And this setup enables us to simulate the phase difference between those two paths. Let's switch to VirtualLab, and I will load the Mach-Zehnder interferometer. And here you can see the light path view of the Mach-Zehnder interferometer I've configured. And at first we have a light source. For the simulation of the Mach-Zehnder interferometer we use a monochromatic helium neon laser. We use a Gaussian type source, and here you can enter some basic parameters like the divergence. This gas laser usually has a very low divergence of about 0.05 degree. You can also enter the spectral parameters. This is the characteristic wavelength of a helium neon laser, and basic parameters and so on. Afterwards there's a beam expander which expands the beam diameter by a factor of 3. This is a simple optical interface sequence where we have different optical interfaces, in this case conical interfaces and materials in between, and they are building two lenses, and this setup is just a Galileo type telescope. Then we have a beam splitter, and this beam splitter splits the light into two channels. And here you can set the ratio of energy which is used to split the light into the two channels. And now I will show you how to set these two channels in VirtualLab. Therefore we go to the light path editor, and in the path tab you can see all the elements you have in your light path view. And as you can see, the ideal beam splitter is listed twice. And you have one entry in your table for each of the two channels. And so you can enter the following element for each of the channels. And for the channel 0, it's the phase delaying plate, which corresponds to our reference path. And for channel 1, it's the ideal plane mirror, what corresponds to the measurement path. After the beam splitter, there are the two paths I already mentioned, and here you can find plane mirrors. And you can see that the positioning in VirtualLab is very simple. We just have to set the Z positions, and the deflection or reflection at mirrors is calculated automatically. When we look into the mirror, we see a tilt angle of 45 degrees, and VirtualLab automatically calculates the direction of the reflected light by regarding the law of reflection. And you see that this is reflected light due to the path is highlighted in red. So you need no further coordinate breaks or something like this to configure such a reflective setup. After the mirrors, you have the beam combiner plane, but this is only depicted here. The real combining and calculation of the interference pattern is done in the screen or in front of the screen, which is what is much more efficient than to propagate the interference pattern to the detector. And this is done here. You can click on the detector tab in the light path editor, and by selecting yes for the sum up of the fields, the interference pattern is calculated. Now we can use the 3D system view to get the first overview of the positioning of the elements we've placed in the light path view. And here you can see all the elements, and yeah, you can see the positioning seems to be correct. And now we can use ray tracing to check the light path, part of the light through our setup. Therefore, we use the ray tracing system analyzer of VirtualLab, and just click go. And here's the result. We get this view, and you see the different rays propagating through our setup and through the two different paths and hitting the screen at the end. So we've set up the light path correctly. Now, we can also use ray tracing to calculate the rays on our screen. You can see this here. But by using ray tracing, we get no interference pattern. This is one of the constraints of the ray tracing engine. Therefore, we now switch to physical optics and use field tracing to calculate the interference pattern. Just click go, and here you can see the interference pattern of this setup. I use some interpolation to smooth the calculated field a little bit, and now here you can change the scale from grayscale to false color or reverse false color as you like to, and you can also select other field components. Now we see the amplitude of the X component of the field. We can also select the Y component or the squared amplitude of each component. We can also see select the phase. Now, if you want to see what you would see in the lab on your screen, you can choose the light view. And this light view calculates the intensity of the light and also regards the sensitivity of the human eye. And now we get the interference pattern as you would get it in the lab on your screen. And now you can do some further investigation. For example, we choose the line marker and do a line selection through the interference pattern, and right below we get the intensity along this line. And what we get is the typical intensity modulation of interference pattern. Now we can further investigate the influence of some deviations like alignment errors of the components and so on. And for example, I would change the positioning of our sample element, and if I go to the positioning of this element, find it here on the positioning orientation tab, you find that there's a basal positioning option and an isolate positioning option. And now I want to explain you the difference between isolated and basal positioning. Now if you have an optical setup where are no tilts, all the components are on one optical axis. Now if you introduce, so light is going straight through. If you have a basal orientation and you tilt, you enter a tilt in the basal orientation tab, then the element, in this case the lens, is tilted, and the optical axis for all the following elements is tilted as well. So the light propagation is changing like this. If you use in contrast, if you use the isolate positioning, just the position or the orientation of this component is changed, where the optical axis is constant. So This is the optical axis in this case. So for the simulation of some deviations in positioning, we use the isolate positioning. And to simulate the influence, we now use, we activate this orientation maybe for variation of the angle. We now use the parameter run feature of VirtualLab. You can click in the ribbon above and now click next, and here you have a table where you can find, in the first column, you find all the components which are also listed in the light path editor and in your light path diagram. I now scroll down to the element we want to vary, and here we have the spherical lens, and now we can choose the parameter we want to vary. Select here the spherical angle in the isolate positioning, and for example we want to vary the angle between 0 and 5 degrees. We can enter here the steps, maybe 101 steps, and VirtualLab automatically calculates the step size. By clicking next, you can see all the steps VirtualLab will calculate during this parameter run. And on the next tab you can select the simulation engine and the detecting device. You use field tracing and the virtual screen. And for 101 steps, this calculation lasts some seconds, and therefore I will just load a parameter run where the results are already calculated. You can see the same variation as I entered before, same detector, and here you can find all the results. So you get one field for all of the different tilt angles. And for 0 degree tilt, we get the same result that we get in the some minutes ago. And now we can check what influence this tilt has. Maybe at 2.4 degree, or it's very similar. Maybe we use this, and you see here that we now have kind of a minimum in the middle of our interference pattern instead of a maximum. And if we go to 5 degree, there's a maximum again. And instead of a simple output of each field, you can use the combined output in this column here, and you can select different types of the combined output. For example, single documents, so you would get all the single documents from the 101 steps, and you can also get an animation. And now we want to see the animation, and by double clicking on this field you would calculate the animation. But this also takes some seconds because you have to convert all the fields into light view and then add it to this video, and therefore I load this prepared animation, and by clicking on go you see the influence of the tilt we've calculated. And you can see the interference pattern changes by changing the tilt angle. Now we can do the same if regarding X-shift instead of the tilt. Therefore we use again the parameter run, and now we choose the isolated translation instead of isolated tilting, and now we're changing the X position of the element between 0 and 500 micron, again 101 steps. Here we see the steps again, choosing the engine and the detector, and here we have all the fields we have calculated. And again for 0 shift we get the same field we had before, and for some shift the field is also shifted slightly, whereas for 500 micron the field is nearly leaving our screen. And again we can choose an animated output, and I will load it and show you the prepared file, and you see with the shifting the element in the x direction, our interference pattern also moves a little bit. Now to summarize the simulation of the Mach-Zehnder interferometer, you've seen we've calculated interference pattern, and before we've done this, I checked the light path of this setup by using ray tracing. Afterwards, we had to use field tracing to simulate the interference pattern and interference fringes, and then we were able to do some investigations like checking the influence of alignment errors, such as tilts and shifts of an element. So the next example I want to show you is the Michelson interferometer. And for this setup, we now use a white light source, and because of this fact, we want to calculate interference, but we have also to regard some coherence effects, which we want to calculate using field tracing. Now the Michelson interferometer is a very famous setup where we again have two paths, two interferometer arms, but in this case they are they have an angle of 90 degrees to each other, and mirror 1 is our reference path, and mirror 2, this is our measurement path. And due to the fact that we're using a white light source, and because of the limited coherence length of this source, we can use this Michelson interferometer as a topography scanning system, as I will show you later on. Now switch to VirtualLab again. I will use the Windows Close All option to close all of the windows we had for our first example, and now load the Michelson interferometer. And here's the setup of the Michelson interferometer in VirtualLab. And here you can see the light source, which is a xenon lamp in this case. And the xenon lamp is a very interesting light source. It has the spectrum of a black body, nearly, and you can see the spectrum I've entered here. You can calculate the spectrum and enter it, load it into the light source, and this is the black body spectrum for a temperature of 6200 Kelvin, for example. And I used the interval, the region of 380 nanometers to 750 nanometers, which corresponds to the visual spectrum. And I discretized this spectrum into 41 wavelengths, which are now entered in this table with a specific amplitude values. Due to the fact that the emitting region of this high pressure gas lamp is very small, we can assume this source as a spherical wave. So we need, afterwards, we need a collimating element, and we use an achromatic lens system here. I just use this Edmund Optics achromat, which you can find on the Edmund Optics website, and import it to VirtualLab. And here you can see it's an optical interface sequence with different optical surfaces and materials. Afterwards, there's again a beam splitter. I explained you the function at the example before. Then we have the two mirrors of the two paths, and again we have beam combiner plane, but the combining and the calculation of the interference pattern is also done at the virtual screen again. And here you can see also that we only need to define the set distance for the setup. So we can again use the 3D system view to get the first impression of our setup, and you can see the source with the collimating achromat in this edge, and then we have the two measurement paths here, the beam splitting and combining in the middle, and here's the screen. And now we can do a ray tracing analyzation first, and due to we chose 41 wavelengths in our source, we also get the simulation of 41 different wavelengths in the ray tracing system analyzation. You can see violet or green and red and so on. And here you can see the spherical wave, which is collimated into our setup. So the setup is set correctly. And now we switch to field tracing and calculate the interference pattern of the setup. And this will take some seconds because now we have to calculate the light propagation for each of the 41 wavelengths. And what we get as result is the field for each of these 41 wavelengths. And now we can select each of the indices of the wavelengths by clicking here, on the right, and we can see all the fields we've calculated. Again, we can also look at the phases and other components of the electric field. And now we are interested in the light view to see the effect of the limited coherence length. And this calculation of the light view also needs some time because again we have 41 wavelengths, 41 fields which have to be regarded. And while this is calculating, I change the spectral parameters to a single wavelength. I use just one mode to have a comparison to a monochromatic interference pattern. Now this is the monochromatic interference pattern, and here we have the interference pattern for our 41 wavelengths. And if we do a line scan again, now we use this horizontal line scan, we can see the difference, the influence of the limited coherence. For white light, we have the typical constructive and destructive interference just in the middle. Here you can see this modulation, while we for unlimited coherence, we have this modulation through the whole interference pattern. And this is the influence of the limited coherence. And this fact we can later use for the topography scanning setup. Now, if I change the path length of the measurement path just a little bit, I deactivate the parameter coupling, I will explain this feature later, I just add 6 micron to the measurement path and again calculate the field using the 41 wavelengths. I have just put it back to the full set of lateral modes. Now calculate again the interference pattern for the 41 wavelengths. And what we expect is if the change of the path length is much larger than the coherence length of the light source, we will see no interference pattern. The interference pattern vanishes in this case. And the coherence length of such a white light source is in the magnitude of below 1 micron. So the change of the path length is in fact much larger than the coherence length. And here we had the result for the identical path lengths, and you get the result for different path slightly different path lengths. And you see the interference pattern is gone. It's vanished, and if I do a line scan, you see no modulation, no interference. And now we use this fact for our topography scanning setup. We'll show you a little slide before, and what we do now is to change the mirror of our measurement path to exchange this by a sample. For example, we use the modified topography of a €1 coin. And by varying the path length of the measurement path, we can use the limited coherence length and set the path length to different height levels, and we only see the maximum of constructive interference if the path lengths are identical. And what we get is that we, for different path lengths, we get different intensity modulations. I will show this in VirtualLab. I close the windows before, so, and load the setup. And here we have the sample file, the sample, which is exchanged to mirror 2, and we have an so-called double interface component where I entered a sample interface. And I will want to show you how to import such a profile to VirtualLab. And you have the sampled interface, and here you can set an imported height profile. You can import it via text file or via bitmap file and so on. And by clicking show, you can see the profile you imported. I changed the interpolation method to linear, which improves the height profile illustration, and here you can see the height profile. We have 3 height level. One height level is the one and the ring, and the second height level is the European continent, and the third height level is all the surrounding. And now we can also get a 3D view of our coin, of our sampled interface. We can change, for example, accuracy a little bit, so it's a little more effort to calculate the 3D picture. And we can change the display mode to intransparent, and we can see the imported height profile here. Okay. Now we can calculate this setup, the light propagation, but due to the fact that now we need a lot of rays, because we have to resolve the structure of the 1 euro coin, we have to use around about 100,000 rays. This lasts a little bit, so I load the result of this calculation, which also takes a little bit. For the 41 wavelengths we used and the 100,000 rays per wavelength, the calculated field is about 1.5 gigabytes, the saved file. And so the calculation and also the loading from the saved file takes some seconds. And I switch back to the slide as long as it loads. And what we now get in this false color illustration is that red is the constructive interference. And if you change the path length of the second of the measurement path, we can scan through these height levels. Here we are the identical path length to the reference path for the surrounding. In the second screen we have the same path length for the continent, and in the third picture we have the same path length for this number and the euro letters. And it's just loading the file. Wait some seconds. Okay, and here we have loaded the file, and now at the moment you can see it's a little bit larger file. So we are ready. We can also change this false color view to maybe grayscale. It's a little bit more intuitive, that you see, okay, where we have high intensity, it's brighter than the surrounding. Where we have low intensity, it's darker. And can switch to false color again to the rainbow. Here you can see this file is very large, so he has to calculate some things in the background. And this is, at the moment, this is yellow because we had automatic scaling. But if you change to user scaling and change to the equal scaling we had in on the slides, about 40, you see we get the same result than in the slides. And you can do this now for different height levels and see the change of the coherence of the intensity. Now to summarize simulation of the Michelson interferometer, we used again ray tracing to set up our system to calculate the light propagation through the setup, and then we used field tracing again to simulate the interference fringes, to simulate coherence effects, and then we applied the setup to scan through the height levels of a sample to do a topography scan. And now I want to show you our last example for today. It's the Czerny-Turner monochromator and spectrometer, and this application is a little bit different than both interferometer we have seen before. Now, in this case, we are not interested in interference and coherence, but we are more interested in diffraction because we are using a grating to split the wavelengths of the light we are using. And of course we also want to calculate the field distribution and field values like amplitude and phase. Now the Czerny-Turner monochromator is a setup where we have a light source and then there's an entrance aperture, and after the entrance aperture the light is reflected onto a grating, and this grating splits, is the Purcell element in this setup, and splits the wavelengths lateral, and now the different wavelengths hit in a second mirror, and this mirror reflects light to the detector aperture. And due to the setup, the position of the systems, just one wavelength can enter the detector aperture. And by changing the tilt angle of the grating, you can now set the wavelength which can enter the detector aperture. This means that you can set the wavelength independency of this tilt. And the function of this setup is such that you can see the picture of the entrance aperture, which is the green box here, and in the background you have the detector aperture. And if you scan with this image by changing the grating tilt over this whole of the detector aperture, you get this power curve. And this is the measurement of this setup, the measurement strategy. And I will show this in VirtualLab. I again close all windows and open the setup of the Czerny-Turner monochromator. And here you can see the setup, the light path diagram, and we have here two sources. We have a plane wave source, which I use for the calibration of the setup, and we have a sodium doublet lamp with a characteristic two wavelengths of the natrium D line. I will show you this the resolving of these two lines as application for this setup. We have after the source we have the entrance aperture, the first parabolic mirror. You can enter here the focal length and some parameters like diameter. And now what is very interesting is the grating element. We're using a blazed grating, but the very special fact of this component is that we are calculating the efficiency of the grating of the diffraction order I've selected rigorously. So we use the Fourier-Moldal method to calculate the efficiency for each wavelength we are using for the setup. And here I've chosen the first diffraction order for the for my setup, and I will want to show you the effect of the different diffraction efficiencies. I've entered 3 different wavelengths here for the setup, and now I want to show you how I can now configure the setup for the imaging of one wavelength, for the measurement of one wavelength, and therefore I use the parameter coupling feature. And this feature you find right above here is to couple different parameters of your setup. For example, you can choose you can choose all the parameters which are characteristic for your setup. For example, we use now the tilt angle of the grating to set our wavelength, and I use the grating period to calculate the direction by regarding the grating equation. And I need also a calibration wavelength, and this is the wavelength where light impinges normally on our grating. And the inspection wavelength I've set is the wavelength which can enter the detector aperture without any perturbation. And by clicking on Edit, you can link the selected parameters by using some C# code. It's I use the grating equation and to calculate the the grating tilt angle by setting the inspection wavelength. And by clicking Next, you can now see here the calculated tilt angle. Now I enter inspection wavelength of 463 nanometers, which is one of the wavelengths I've entered in the light source, and I will now show you why I use this wavelength. And now we get this image of the entrance aperture, and now I change the inspection wavelength in the parameter overview to 496 nanometers, which is one of the other wavelengths of our source. And now we see nothing here, but each of the windows has the three wavelengths of our source. And now we change to the second wavelength, and here we have the first wavelength. Now you can see we have two different wavelengths. And I change to user scaling, and now I copy the scaling from the first window to the second window by using the Copy View Settings button. Click OK, and you see if the scaling of the field is the same, we have a lower intensity for the second wavelength. And this is the effect of the rigorous consideration in this grating component. So now we can use this setup, for example, to scan through the different wavelengths. But first I will want to show you again a 3D view of the setup. And because we use very long paths in between the setup, you see it's 1 meter between all the elements, the path is very long and the elements very small. You can improve the view, the illustration, by reducing the Z distance by a factor of 0.1. And you can see now the setup. Here we have the two mirrors here. We have the source and the entrance aperture, the grating, and here's the detector aperture and the screen. And we can do, again, ray tracing system analyzation. Again, we have 3 different wavelengths in our source. And what we see here is that the polychromatic light enters mirror 1, is reflected onto the grating, and the grating splits the 3 wavelengths to mirror 2, and just 1 wavelength is reflected to the aperture of the detector and hits the detector. And this is the strategy of the setup, as I mentioned before. And now we can use the parameter run feature again to calculate a scan through the visual range, but this calculation also takes some time, and I will just show you an animation. So I just use a white light source and then changed the inspection wavelength of the parameter coupling in the parameter run and choose again an animated output, and what the result you can see here. And you can see the light on the detector changes from violet to the visual spectrum to deep red. And at last I will want to show you the application that we can resolve the sodium doublet by using this setup. I close this window and load the setup, and we can do this by doing a parameter run. We now choose the sodium lamp by toggle the light source, and then to do a parameter run over the inspection wavelength, and you can see the range of the variation is now very small. We have just 588.4 to 590.1 nanometers and use a lot of steps, 171, because the the difference between both wavelengths of this doublet is just 0.6 nanometers, what corresponds to a frequency difference of about 500 gigahertz just. So the step size is about 10 picometers. And here are the steps we're going to calculate. We're choosing the engine and the detector. We use now a power detector, and this calculation needs some time, and therefore I've prepared this. And you see for some wavelengths we get some power on the detector, and now I will output these values in a figure by double clicking here, and now we can see this power curve, and we see I've shown you the strategy of the setup some slides before, and then we get this power dependency for one wavelength, and here you can see the second wavelength. That means that due to this dip, we can see this dip, and this means we can resolve the two wavelengths with our setup. And if we change the inspection wavelength to this dip, we can also see both wavelengths on our screen. I prepared a light path diagram. I click just click go, and what we get is the field with again two wavelengths, which are the characteristic wavelengths of the sodium lamp. And now calculate the light view, and what you can see here is that the first wavelength, which corresponds to this rectangle, is just leaving the aperture of the detector, and the second wavelength, which has typically a lower intensity, just entering the aperture. So the resolving is not completely, and due to this fact, the intensity the power we have calculated not reach zero in this case, but the resolution is good enough to resolve these two wavelengths for our setup. Now, to summarize, you've seen we could set up the Czerny-Turner setup, the monochromator and spectrometric. We've done some monochromatic and monochromator and spectrometric investigations, and we can do an analysis by using ray tracing, and then calculate the light propagation by using field tracing. We can investigate the performance of the setup, and this investigation also includes the rigorous calculation of the diffraction efficiency by using the Fourier-Modal method in the grading component. And we were able to resolve the characteristic wavelength doublet of sodium with the setup. Now, to summarize the whole webinar, we've seen that we have a lot of benefit if we're using different light propagation techniques for simulate such complex systems. So we were able to simulate interference, coherence, and diffraction effects. You've also seen that the positioning of transmissive and reflective components in VirtualLab is very easy. You have not to configure extra components like coordinate breaks or something like this. You can also determine the influence of tolerances, maybe positioning, alignment errors, or something like this. And you can also evaluate your calculated results.